Okay, let's get started. So hello, everybody. Welcome to the session. I'm really happy to have everyone here. Today's session is going to be about Retrieval Augmented Generation, or otherwise known as RAG. With me, I have Nitin Rag, the head of product growth machine learning at Databricks. My name is Roy Schwaber-Cohen. I'm a developer advocate here at Pinecone. Just a couple of items here just to set the scene. We have a QA section for this session. So if you have any questions during the session, please leave them there. We will do our best to answer all of your questions, but most likely we're not going to get to all of them. If we don't, please feel free to join our community on our forum for Pinecone, and we'll do our best to follow up there. And with that, let's get started. Okay. So let's go over our agenda for today. We'll have 5 sections and then a Q&A and potentially tips or tricks at the end, depending on the time that we have. We'll start with a basic intro into what embeddings are. We'll then touch on what vector databases are and how they fit in this picture. Then we'll take a deeper dive into Retrieval Augmented Generation, which is the topic of today's talk. And then specifically, we'll go into how Databricks works into that, what their GenAI capabilities are. That portion will be done by Nitin, and Nitin will also walk us through some of the code that demonstrates the creation of a RAG application using Databricks and Pinecone. Like I said, we'll have time for a Q&A, and if time allows, we'll go into some tips and tricks that we've encountered to be helpful for building RAG applications. And without further ado, let's jump right into it. So let's talk about embeddings. Many of the AI models that we see out there these days basically mimic the behaviors of the human brain. Obviously, they're not exactly the same. There are substantial differences, but like the architecture tries to imitate life in a lot of ways. And the most commonly known data structure for these is a neural network. And these neural networks are basically made up of these interconnected, quote unquote, neurons, artificial neurons that are arranged in consecutive layers. And what happens is that these networks learn from a huge amount of data that they're exposed to. And over time, the connections between the layers of these artificial neurons are being updated over time. And then once these neural networks are trained, they're capable of extracting high-level features from the data that they've been trained on, and then make decisions or predictions based on that data and based on the task that they were trained to accomplish. These features, these high-level features, are represented as vectors, basically long lists of numbers. And these vectors are usually high-dimensional, which means that they are very long lists of numbers. In a lot of cases, it could be thousands of dimensions, which means that it's basically an array with thousands of values. And we call these representations embeddings. So let's talk a little bit about what these embeddings are. Essentially, embeddings are a numerical representation of some relationship between discrete objects like words or sentences or documents. So basically what happens is that once the embedding model is trained, it is capable of taking the relationship that exists in, for example, semantic space and embed it, or essentially project it into a different space. And in this case, it is a continuous vector space. And that's the source of the word embeddings. And essentially what these embeddings allow us to do is to apply mathematical utilities, and we'll talk about those a little bit later, to anything that has meaning. And we'll see how that works as we go along in this talk. That basically opens the door to all sorts of interesting applications like semantic search, image search, long-term memory for conversational agents, and more. So it's very hard, nearly impossible, to actually visualize a high-dimensional vector space, because again, there are thousands of dimensions. We can't quite visualize thousands of dimensions. We can only visualize up to 3 dimensions. And so this is a very simplified representation of what actually happens within an embedding space. So in this example, I have a set of embeddings here represented as these blue and yellow balls. And these are all embeddings that live somewhere within this embedding space. And what we see here is that embeddings that are of concepts that have some sort of semantic similarity are clustered together and are close to one another. And other embeddings that have less semantic similarity are farther apart from one another. And that's the strength and the thing that basically embeddings enable us to do. They enable us to apply geometrical measures to basically see whether a concept is related in a meaningful way to another concept or similar to another concept. And we can do that by just checking essentially its proximity to another concept. So embedding models are not limited to only looking at particular words or concepts. They're actually helpful in contextualizing meaning. So a lot of the times, the meaning of any particular word is informed by the context that it lives within. So for example, we can take the word bank and we can take the 3 sentences that this word bank appears in. Where is the Bank of England? Where is the grassy bank? And how does a plain bank? And the meaning of the word bank is actually informed by the sentence that it lives in. And so because the meaning in each one of these sentences changes the meaning of the word bank itself, the embedding for the concept is going to be farther apart in the embedding space. And then conversely, if we're looking at sentences that are using different surface forms completely, but have the same meaning, those sentences are going to be embedded within a similar space within the embedding space. So here we have the bees decided to have mutiny against their queen, and defying stinging insects rebelled in opposition to their matriarch. Both of these mean exactly the same thing, using completely different surface forms, but are going to be close to one another in the embedding space because what we care about here is the contextualized meaning. Okay, now that we have some idea of what embeddings are and how they work, let's talk about vector databases. So a vector database basically makes it easier for us to manage vectors like embeddings, but do it at scale. So many of you may have heard of different types of vector indices, for example, FICE and others that basically live in memory. A vector database is built to scale way up than what your memory limitations might be and enable applications that rely on the operations that a database might have, like low latency CRUD. So your inserts and update and delete are going to be fast and efficient. And then it also enables other type of utilities that are, again, common to databases that kind of make the interaction with that database a lot easier. For example, batch processing. Another thing that vector databases do that is unique to vector databases and not other databases is that they optimize the similarity search of the vectors that they store. And they allow you to apply different similarity metrics like cosine, Euclidean, and dot product metrics to actually retrieve the vectors that you're interested in. And a very critical capability of vector databases is their ability to associate metadata with each vector that is stored in the vector database. And that basically allows us to do 2 things. One is to enrich the context that is associated with that vector. So we can now have some structured data associated with this vector representation of the embedded content. And it also allows us to filter through our vector space to basically make our queries a lot more efficient. So one of the ways that we can think about vector databases in the context of RAG and in other AI applications is what they do in relation to the AI model, right? So the AI model, in essence, is a black box. It tells us what the result is, but it doesn't tell us why the result is why the result is what it is. So in the case of LLMs, we don't even get a confidence level, right? We don't have any understanding of why the prediction or the completion that the model has provided us is what it is. And vector databases allow us to have a deeper understanding of how the model works. And more importantly, they allow us to attach some trusted handle onto the world of structured data, meaning we can associate the embedding with some structured data. And that basically takes away the responsibility for the explanation part away from the model, and it puts this in our hands, right? It allows us to basically say, when I have some embedding that I'm retrieving, I know for a fact that the data that I associated with it is trusted to a certain degree. And I'm not relying on the model to tell me exactly why the response was the way that it is, because I provided that information myself. A word about Pinecone in that context. So Pinecone is a fully managed, distributed, and high-performance vector database. It was built from the ground up to deal natively with vectors, and it allows us to basically build vector applications that rely on vector applications at scale. starting from millions, but up to hundreds of millions and billions of embeddings, all while maintaining very low latency, both for querying and for writing, and getting those writes basically appear in the index very quickly. And of course, it is optimized for performance and cost, such that it is a feasible thing to build, again, applications that deal with billions of embeddings. Okay, now that we have an understanding of embeddings, vector databases, and how they work together, let's tie together and talk about retrieval augmented generation. In general, we can talk about generative AI models and how they work. The basic premise is very simple. You give a generative AI model some prompt, and it's going to generate some content. That content could be text, that content could be images, it could compose music for you, it could do all sorts of varied things. But the core limitation of a Gen AI model is that it is limited to the data that it was trained on. So that data might be the entire internet, but it's not going to be your company's intranet, right? So there's not going to be any proprietary information that is not public in any of the foundation models that are out there. And that basically causes these models to behave in a way that sometimes might be desirable and sometimes might not be desirable, which is that they hallucinate. And that means that the model is going to do its best to give you a response that sounds plausible, that sounds realistic, but it might not be grounded in the input data that you provided it, meaning it will try to invent an answer no matter what, right? And again, in some cases, like a creative case, that might be a fantastic kind of behavior. So if you wanted to write you a new poem, that's great. But if you're trying to have it answer a question that relies on your company data, that might not be a very desirable behavior. So how do we fix that? So the retrieval augmented generation technique basically tries to mitigate this problem. And it does that by trying to provide some anchor to real world structured data. So basically what we have to do in order to accomplish this is to create an embedded knowledge base. So that means that we take our knowledge base, create embeddings for it, and upsert it to our vector database. We then query the database with a user's prompt. So we take the user's prompt, embed it, and query the database, and retrieve semantically relevant content. This is important because, again, RAG applications usually live in the context of a natural language question. So a user would prompt the system with a natural language question. And since we are in a natural language context, we would like to take that and leverage it as much as possible. And using the abilities of the vector database to produce semantically relevant content is the most natural thing to do in this kind of setting. The vector database doesn't only provide us with semantically relevant results, it can also basically control what type of information any particular user can and cannot access. And of course, filter the information that they are looking for depending on the requirements of the application using metadata. And once we have the relevant content, we can take it and inject it into what's called the context window of the large language model. So any large language model will take a prompt, and part of that prompt could be this semantically relevant content. And we basically use prompt engineering to tell the model to actually use that content in order to build its future responses. So let's look at how these applications are typically architected. So in many cases, we are interacting with content from the web, but this is not necessarily the only way of interacting with it. This is more to foreshadow the demo that Nitin is going to present to us a little bit later. We basically start with a list of resources, the URLs, for example. We have a crawler basically grab the content from those URLs, and then we have our web pages. We take those web pages and we ideally clean them out of all the HTML noise, and then we do what's called chunking, which is basically breaking those web pages into chunks that are small and contextually relevant within themselves. And then we take those chunks and we pass them through the embedding model. The embedding model produces vector embeddings that are associated with some metadata. That could be either something that is based on the content of the chunk itself, or the source that it came from, or any other relevant piece of information. Then that content is passed through the API and saved in the vector database, in this case, Pinecone. When we're ready to consume this content, our application will issue a query. That query will be embedded. We can then use a metadata filter, if we so choose, to scope our query more specifically. We pass the vector embedding for that query that we got from the user, and then get back a result that will include both the vectors and the metadata associated with those vectors. We can then do whatever we want with that metadata. For example, the chunks themselves that are semantically relevant, and again, or the URLs that they're associated with, or the resources that they're associated with, and provided back into the context window of the LLM. That is passed into the LLM to get back a full response, and that is usually streamed back into the application. So that's RAG in a very short kind of description, but let's talk about what happens when we deal with these kind of scenarios at scale. So when we build RAG applications for very big knowledge bases, we're inevitably going to have to think about how we deal with creating embeddings at scale and managing them at scale. And even if we only have millions of documents, when we create chunks for all of these documents, we're going to have potentially hundreds of millions and even billions of chunked pieces of data that are going to have to be embedded and then have to be inserted somewhere and then used downstream. And we also have to consider the fact that we want to keep our knowledge base up to date. And so this has to be some sort of a continuous process that keeps taking these documents, chunking them and embedding them, and then updating them as necessary in the vector database. So what are the challenges here? First, generating embeddings in and of itself is a compute-intensive process. It requires GPUs for the most part. And it's really hard to tackle these type of problems when you're trying to do this on your one machine, and unfeasible, again, when you're dealing with these kind of high-scale loads. And many enterprise scenarios won't allow you to use just any model any third-party model off the shelf, like OpenAI, et cetera. And you'd have to have some ability to generate those embeddings yourself within the confines of your environment. Of course, data sanitization is something that you can't skip that, especially when you're getting content off the web or any kind of source like that. There's some level of cleaning and data wrangling that you have to do. And again, these processes at scale become very complicated. As I mentioned before, continuous processing is not an easy feat if you're trying to do it on your own. Figuring out the deltas, what updated, what didn't update, what's stale, what's not stale, those are very complex tasks. Then, of course, to store and query these vector embeddings that once was created, you're going to need some specialized store, wink, wink, to handle this massive load. And not all stores are capable of doing that. The ongoing updates need to be written quickly, so you can't afford long delays between the time where you found something that needs to be updated until the time where downstream applications can actually reflect those updates. And to sum it up, basically, traditional solutions like the one you'd come up with on your own using just like a Python notebook running on your machine are fine for small scale. When you're dealing with thousands of documents, those are going to be fine. But for larger scale, we really need to rethink the architecture and consider what tools we're using. And with that, I'd like to pass it on to Nitin to talk about Databricks' generative AI capabilities that will lead us into understanding how we can build our RAG applications on Databricks. Nitin, take it away.
Yeah, thanks, Roy. Hi, everyone. I'll be quick with my slides and want to spend most of my time doing the demo. So yeah, let's start. So quickly about Databricks. Databricks provides a unified Lakehouse platform where you can store all your structured, unstructured, semi-structured data, govern it through Unity Catalog, which is our governance layer. You can govern models, Python functions, data tables, as well as any of the other assets through a unified layer. While Lakehouse AI provides many features for classical ML, today we are only going to focus on generative AI and how to quickly build an LLM application. And I've seen customers using Lakehouse AI for building an LLM application and going live in a matter of days or weeks. So there are three important capabilities when you think about generative AI applications. Again, it all starts with data sets because a lot of these models are already available on SaaS. You're not fine-tuning, but it still starts with data sets. So first capability is how do you collect this data that is needed for your RAG applications, and how do you prepare it for loading into vector store like Pinecone, and also how do you store the context along with it. And second is, what are the different avenues to access your SAS models? How do you evaluate those models against each other? And then if you need, how do you do fine tuning? And as you try to go to production, build the production grade applications, what are the capabilities we provide when you put those applications in production so that those applications run in a scalable infrastructure, as well as you are able to evaluate and monitor them in the production. Let's move on and let's talk about how Lakehouse AI provides those capabilities. Next slide, please. Right. Awesome. Back in June, of course, Databricks has been innovating in this space for quite a while, but back in June at Data and AI Summit, we have announced many new capabilities. A lot of these capabilities are either, of course, generally available, some are in private preview and some are in public preview. So like real quick, in the data sets, we have, of course, partners like Pinecone who can provide vector search. We have launched online feature serving. Sometimes it becomes important to augment your vector capability, vector like embeddings to augment the context that you send to LLM. And then Databricks provides many toolings such as Spark, PySpark, Scala, so that you can collect and prepare your data on the Lakehouse. Then in the model department, we have, of course, curated AI models other than SAS models. We support and help optimize these curated state-of-the-art AI models for embedding as well as LLMs. One of the examples is Llama 2. Then for model fine-tuning, we have AutoML capability, which makes it easy to fine-tune a model. And then MLflow is our MLOps platform that's downloaded by 13 million times. It's open source. So we are adding a lot of capabilities for MLflow, like model evaluation for LLMs, MLflow. On the production side, we have MLflow AI Gateway. That is an API gateway for connecting to your SAS LLM ecosystem. We just went live, or live as in public preview, with our model serving for GPUs, where you can serve optimize LLMs such as Llama 2 and MPT. And then finally, we have Lakehouse monitoring to monitor your models and your LLM applications once they are in production. So let's quickly go through each one of these and then jump to a demo. Okay, next slide. Awesome. So on the model side, we have, while you can use your favorite SaaS platform like OpenAI, Anthropic, and others, but we support and we recommend some of the state-of-the-art model for embedding, creating text embeddings, creating image embeddings, as well as LLMs that are state-of-the-art, such as MPT, that is invented by Mosaic ML, acquired by Databricks, as well as Llama 2, which is probably most popular model in last few weeks. So these models, we make it accessible easily through Databricks. Of course, you can bring any of the Hugging Face model, but then we also make sure that these models run optimally in our model serving infrastructure so that you can get better token latency as well as higher throughput. Next slide, please. Awesome. So if you want to fine-tune a model, and this is, again, advanced stage, you typically start with prompt engineering, you build a RAG application, and then sometimes you also want to fine-tune a model so that the model understands your domain-specific vocabulary. Sometimes it becomes very important. We are seeing a lot of customers doing this. So we have actually added or enhanced our AutoML capability to fine-tune LLM models. So all you do is supply your data, you select some of these gears like training cost limit, serving cost, what quality metrics you're trying to hit, and then what is your latency. And based on these inputs, we fine-tune a model and create a optimized serving endpoint for you. Currently, it supports token classification in private preview as well as embedding fine-tuning. Okay. Next slide, please. Now, what about comparing models? This is a very active problem because everybody wants to understand which model is better for my particular domain and my particular problem area. So can you, next slide? Yeah, so MLflow is our MLOps platform. It's also available in open source. So we are adding a lot of capabilities into MLflow. We have recently added in MLflow 2.7 MLflow evaluation, where you can hit any of these models and we start logging prompt requests and responses. in MLflow, prompt runs, and then you can visually compare, okay, my prompt, same prompt request against a variety of models. What is the response? And then you can visually inspect that, compare that, so that you understand what's the best model. We have also recently added like some of the quantifiable scores like toxicity, perplexity, so that it can compare your model against some of the standard human benchmarks. And we will continue to innovate so that you can get, as you're developing these models, or as you're developing your generative AI applications, you can quickly compare against different models through MLflow evaluation. Okay. Yeah, so this is MLflow AI Gateway is a very important thing if you think about productionalizing these generative AI application at scale, right? When you're doing like a single applications, you worry about productionalizing this application, but as an enterprise, you will have multiple people, multiple teams, and multiple applications trying to build infused generative AI applications, and they will be trying to hit a lot of these third-party SaaS platforms. So MLflow AI Gateway becomes your central gateway for managing credentials of this third-party SaaS, caching the request response. It can log your prompt request and response for governance as well as security, and then it will also provide rate limiting and cost limiting as a single solutions. It is available on Databricks as a managed service, but then you can also install this because this is also available in OSS. Pretty awesome. You can connect to any of the SaaS providers or also Databricks model serving for the custom model. Next slide. Awesome. Now, let's say you have developed the application, and I'm going to walk you through a complete end-to-end demo. What about production? When do you go to production? What happens? Next slide, please. Awesome. Other than your favorite SaaS APIs, right? OpenAI, Anthropic, and others, sometimes you also want to try out the open source model, such as Llama 2 is MPT7, and the performance sometimes is on par for your specific problem, right? You may not need these massive giant models that SaaS platform provides. So what Databricks provide is an optimized model serving, where what we do is we have under the hood, we have created optimized tool chain based on the model base, such as MPT is a model base, Llama is a model base, Whisper is a model base. And each of these models have a very specific optimization technique to improve the latency of the tokens, the token latency, reduce the token latency, and improve the performance or throughput so that you can optimally use the GPUs. So it's very easy. All you have to do is save your model in MLflow, register your model in MLflow with a certain tag that allows it to use the optimization toolchain. As you create the model endpoint, you get these optimized models so that it can give you 60% or more better throughput and then lower latency per token. Next slide, please. Now, once you're in production, you start worrying about, hey, how my model is performing. So we have also in public preview launch Lakehouse monitoring, which can not just be used for generative AI, but for any common or general purpose machine learning pipeline. So what it does is it provides you, it monitors your data assets and your models for drift as data drift and concept drift, and also provides you root cause analysis, because with Databricks, it's a data and AI platform. So it can monitor models, features, your training sets, ground truth, and then all the gold, silver, and bronze tables, and then provides you the root cause where that particular pipeline failed, and that sort of generated that data or model drift. Okay. So with that, let's go back to the generative AI application architecture that I'm going to demonstrate, and then I'll walk you through the notebooks. Awesome. So very simple problem. We are going to, in the demo, go through, we are going to scroll docs.databricks.com. This is our like docs website, because I want to build a chatbot where I can ask a question about Databricks documentation, and it should be able to give me that answer. Again, this demo is already available on Databricks website. I have repurposed that to work with Pinecone. And then we will release this example along with the blog post in coming days so that you can try this out. So it has two parts. One is how do you prepare the data so that it is ready to load into vector database, Pinecone vector database. And then the second part is how do you build a generative AI application where you can just ask a question and it should be able to invoke all the logic. The logic here on the right-hand side is you ask a question, it creates an embedding. It creates an embedding. Then it then looks up Pinecone vector database relative context. Then it constructs the prompt, send it to one of the SaaS LLMs via Databricks AI gateway, and then provides you an answer. And how do you productionalize? By setting it as a model endpoint. Okay. So with that, I will take over. Give me a second. So, okay, I hope you can see my screen. So I have a three-part notebook, three-part demo. So there are three notebooks on Databricks environment. You can quickly sign up with Databricks trial workspace. This example is also available on Databricks dbdemos.ai, but I have repurposed it so that it works with the Pinecone. Okay. So the first notebook, I think data preparation is very important when you are building a RAG application. If you already have your data chunked, stored in some sort of data store, then you can skip this notebook, but I will walk you through what is the value of data preparation. Okay. Now, the first thing is in this notebook, what I'm doing is like we're just installing some dependencies and boilerplate code. Then second thing I'm doing is extracting these pages from Databricks website through a sitemap. Now, once the pages are extracted, I'm going to store them in the raw documentation delta table, which is a Lakehouse table. Now, as you can see, I'm showing you the table. It has the raw HTML elements and then URLs that from the sitemap that they have been extracted. Now, if you can see here, LLMs, for your LLMs, you don't need like these raw div tags and HTML tags. They do not provide any meaning to your LLMs, right? So in fact, if you continue to use them for creating your embeddings, first thing is it's gonna increase the size of the embedding, so you have to truncate them. And second is as you send them these HTML tags as context to LLMs, you're gonna spend more money because each of these SaaS providers charge you by tokens, right? So first thing you want to do is clean up these HTML tags because they are meaningless for providing a context for your LLMs. Okay, so that's what we are going to do. So we are going to read this table, the raw table. Second is we are also going to start chunking because these Databricks, these documents can be very large. They can be up to 10,000 tokens, but then you don't want to create embeddings on a very large document because sometimes you can lose the meaning or when you try to search on a very large chunk of data, you may end up getting more than you require that you want to send to your LLM. So you want to right size it. And again, I think Roy is going to talk about what is the best practice when you do chunking. But here, what we are doing is we are using the tokenizer. Every LLM provides you a tokenizer. Since we are going to use ADA 2 for embedding creation, we are going to use GPT 3.5 Turbo as a tokenizer. And we are going to truncate our chunks up to 4,000 tokens only. Okay. So this code here, I'm calculating the token counts based on Turbo GPT tokenizer. Then in this code, I'm splitting the data and removing and cleaning up those HTML tags because I just want to keep the clean data that does not have HTML tags because they do not offer any value. And finally, again, there's a cleanup code. And then finally, after the cleanup, I save the data in a gold table called Databricks documentation. This is a delta table. And as you can see, there are three things. There is an ID. There's a URL from where this particular piece of chunk came from. And then there is a content. As you can see, this is all cleaned up. It does not have any HTML tags, and it is now prime for loading into a vector database. And that's it. Now let's move on to the second topic of creating vector search index. Now, what I've done is before creating vector search index, Pinecone is super easy. Literally, it took me like 5 minutes to define an index, sign up for an account, define an index, and it gave me an endpoint and also the token, right? So one thing you need to have ready is what is your dimension. because your embedding typically has a dimension, and that dimension is determined by the embedding model that you're using. And so since I'm using ADA2, I just quickly ran the dimension, or you can also look up the documentation to figure out what is the dimension, because your vector index will require the dimension. Okay. Now I have created my Pinecone instance. Now let's go to the second notebook, and I'll be very quick. I know we are running out of time. So in this notebook, what I'm doing is boilerplate code. Then first thing I'm doing is like creating an endpoint so that you can create these embeddings as a real-time manner. And this may not be needed for ingesting embeddings, because typically that's a batch application. But when you query, you need some sort of real-time endpoint so you can create an embedding for your questions when you ask the questions. And so this code is like wrapping the OpenAI's ADA2 model as a real-time endpoint in MLflow and then Databricks, right? So what this block is doing is so MLflow also supports OpenAI as a model type. So it just wraps the SAS API as MLflow model. So as you can see here, it's logging the model into MLflow. Then once the model is logged and registered, you create an endpoint, and this is an embedding endpoint. The endpoint name is DB demos endpoint embedding endpoint. So you get a REST API endpoint that you can query, pass the text, and then you get the vector. Okay, so in this block, I'm just testing that particular endpoint. So as you can see, I'm passing the test sentence, and I'm getting a vector, right? This is embedding vector. Now, next thing is I want to create my Pinecone index and then load all my data and metadata into that index. Okay, so I'm importing Pinecone, initializing the API key. It's a good practice to save your API key in some sort of secret store. Then, yeah, this is my index that I have already created in Pinecone. Of course, you can create the index also through the API with Pinecone. Then all I'm doing is now loading the Databricks documentation clean table that you have seen as a data frame in Databricks. Then looping through the rows within the data frame, and then again creating embeddings, right? Creating the embeddings for the content column. And then I'm also constructing a metadata that consists of a URL, content, and title, right? And content is nothing but my chunk. This is the most important thing, because ultimately when you do the query, you want to get the chunk, right? And this is what will become the context. And then with this simple API call, I'm able to load my vectors along with the metadata into Pinecone. Now, again, this is not very efficient way of loading this data. Pinecone also has a Spark connector, which can, because typically in production scenario, you will have millions of such embeddings or millions of chunks. So that you should definitely use this Pinecone connector, which can parallelize and use the power of Spark to load or batch write those embeddings into Pinecone database. Now, when we release this example, we will switch this novice way to the right way of doing this. And you can also use DLT pipeline, which is Databricks' way of ingesting this at scale. Okay. Now, here since I have these embeddings, I'm just querying. I have loaded the embeddings into Pinecone. I'm just querying based on the question. So this is my question. I created an embedding of that particular question, and then send that embedding to DB demos index, which is Pinecone index. And with the query API, I'm just asking it to return one top index, top match. And then also, this is important, include metadata, so that it also, when it returns, it returns the metadata, which consists of ID, content, and URL. As you can see, it's able to hit that index and retrieve the metadata. Now my Pinecone is working. Let's move on to the RAG application creation. So this is notebook 3. Again, this notebook wraps your entire logic into MLflow API or MLflow model, and then sets it as a MLflow Bricks model endpoint, so that you can use any of the conversational chatbot interface to hit that, ask a prompt, and then it will execute all the logic. Okay, so again, importing MLflow gateway. This MLflow gateway, we talked about AI gateway, and then Pinecone client, boilerplate load. Now, this is an important concept. So Databricks or MLflow AI gateway provides you this concept of route. So I'm going to define 2 routes here. One route is to hit Mosaic ML. Mosaic ML is a company acquired by Databricks, and we host a Llama 2 70B model, which is similar to OpenAI. It's a Llama 2 70B model that's hosted as an API. So I'm going to define two routes. First route is to hit the Llama 2 70B completion model. And second route is to create your embeddings through the ADA2 model hosted on OpenAI. Now, both the routes are natively supported in AI Gateway. So you do not really have to write any code to make this operationalize. All you do is the first route is, hey, this is the Mosaic route. This is the API. This is the model that I'm going to use, right? And this is all part of the AI Gateway inputs. This is the provider, and then these are my credentials. So this route is set up. Second route is creating embedding. So this is the path, route type, embeddings. This is the ADA2 model, provider is OpenAI, and then this is the configuration, which is nothing but API key. Now, what happens is, so these routes are now OpenAI, the Databricks AI Gateway is already integrated with LangChain. So imagine instead of LangChain API hitting the OpenAI or Mosaic ML or any other type of SaaS, it'll hit this AI Gateway. AI Gateway has these routes. So in LangChain, instead of hitting that OpenAI as a provider, you will hit AI Gateway in Databricks as a provider with the route. So LangChain will implicitly determine what is the underlying provider, and it will hit it. The nice thing is then you can swap these routes based on your need, and then as these state-of-the-art models evolve, okay, without having to change your generative AI application. Now let's try out the AI Gateway. So we have defined two routes. All we are doing is like querying. First route, which is Mosaic ML 70 completion with the prompt. And second is we are just trying to create the embeddings. So this piece of code responds the prompt and then also responds the embeddings. Now we are ready to deploy generative AI application. Now in this section, what we are doing is we are wrapping all this code as another ML flow model. So then I can host this model as a API endpoint that you can consume as a REST API service. Super easy. Now, within this model, within this particular ML flow model, we need first step is you get a question. First thing is you create an embedding. So that's the embedding logic. Second is once you have created embeddings for your question, second is you want to find relevant documents or chunks from Pinecone. So this is the query logic that you have seen in the other notebook. And then we have this predict function. It glues everything together, right? So the glue is you get a question, input question, and this is like a standard, like a system prompt that is understood by Llama, right? So all you do is find the relevant chunks from Pinecone, append it to the prompt, okay, and then call the Llama 2 70B Mosaic ML endpoint using the prompt and the context, and then it retrieves the response. Now, let's say this ML flow model is built. I just want to quickly test this model before I deploy it as an endpoint. So this is the predict method. I pass the question and I get the answer. It means my code is working. And now I'm ready to deploy it in production. All you do is register the model in ML flow model registry. In this case, I'm using Unity Catalog, which is like a centralized model registry for your Databricks account. I register the model and then I deploy that model as this DB demo chatbot RAG endpoint. And then now it is available for you to call using REST API. After this model is registered, you can then quickly test out with any sort of REST API endpoint. So this is the invocation URL, and then you are sending some sort of question. And this is my question: how can I track billing usage? And voila, you have the response, which is much more accurate than the prompt you would send without a context or without any supporting context. And then this is the debugging context where this is the prompt that we have sent. As you can see, it has the boilerplate prompt, and then it has all this context that is retrieved from Pinecone database. Just to recap, before I pass it back to Roy, you'll be able to use this example to build a end-to-end application with Pinecone and Databricks in matter of minutes, and then matter of probably an hour. And then you can customize with your data and your model and go from inception to production in few days or a week. Now, just to recap what we did, we ingested data, cleaned the data, stored the embeddings into Pinecone along with the metadata. which are chunks. Then we use LLM AI gateway to define a couple of routes. One is Llama 2 and embedding creation. Wrapped all this logic into another ML flow point and served as a REST API that you can query from your own application. Awesome. So with that, this was a demo. You will see the recording. We'll send you the asset. So hopefully you do a happy building. RAG. Share that slide.
Yeah, I think we're actually going to be done with the slide. We have about 6 minutes left with over 100 questions in the channel. I'm not very confident that we're going to get to all of them, but I do want to get to some of them. An anonymous attendee asked, how is metadata processed? Is it vectorized as well? The answer is no, metadata is not vectorized. It's stored as a JSON blob and handled separately from vectors. I had a question here that I really want to find. It's a little bit spicy, but I think it's going to be helpful for people to understand. From Mega Lagrave, I hope I'm pronouncing the name correctly. And this is for you, Nitin. How expensive is Databricks? I'm working on a project estimate right now. Which is the best way to get connected? So I don't know if you want to talk about specific pricing, or maybe you do. I don't know. But how do people
Databricks
get an understanding of pricing?
If you're building a RAG application and you're not really using any of the custom models that are hosted on Databricks, this is super cheap, right? Databricks is not really making anything. It's merely helping you connect your data to your external SaaS ecosystem and helping you build this generative AI layer. So if your data is in Lakehouse, use all this capability. Use Lakehouse, the AI gateway to connect to external resource. Use Pinecone for creating embeddings, and use Databricks ability to clean and prepare data so that it can be used for generative AI application. So these, if you're using Lakehouse for storing data, it doesn't take a lot of dollars or $DBs.
Nice. Cool. Another question about Databricks from David Sullivan. Is Lakehouse monitoring only for Unity Catalog, or does it support Legacy Hive as well?
So Lakehouse monitoring requires Unity Catalog. But then we also have a feature called external tables. So Unity Catalog can connect to your external Hive metadata store using those external tables, and then it becomes a unified layer. We are using Unity Catalog because Unity Catalog provides storage for your models, send Python functions, your data and features. So it's very easy to then track lineage across the different resources.
Gotcha. Okay, I have a question here about RAG from Wayne Culbreth. Sorry, again, I'm butchering names here. Our biggest hurdle with RAG is query formation mid-conversation. Initial queries are easy. As conversation turns continue, we have a hard time getting the right RAG query based on conversation history and most recent prompt from user. We're summarizing conversations with LLM text prompts, but just not getting the output that we want. Any best practices, engineering prompts, etc., you can recommend? We're building direct, i.e. not LangChain, to tackle this very issue. So I have some thoughts about that. There are some techniques of enriching the data that you have. Again, using LLMs is one to basically build queries ahead of time. So potential queries for your chunks, right? So instead of thinking about it as I'm going to try and take the query and directly correlate it to a chunk, I'm going to actually build prior to any kind of user interaction. I'm going to build these queries that are going to relate to a particular chunk. And then I'm going to try and associate the user query to a generated query with the hopes of getting a higher hit rate for any kind of continued conversation. This is one method to go about this. Of course, this is, again, self-query, basically using the LLM to generate additional queries for you. But again, this is like, RAG is yet still an evolving art. I don't think that there's a clear kind of scientific answer to how to deal with these type of difficulties. It's a lot of trial and error. What I would say is like that you'd probably benefit a lot from having like good monitoring and testing methodologies to see like how in fact your recall is performing. What are your precision rates? Are you hitting the relevant documents? And of the relevant documents, how many are hit and given any particular query? And that will help you adjust whether or not you have to add more semantic space around the chunks that are relevant. We have 1 minute left. I'm going to take one last question here and then we'll conclude. Let's see. I marked one more question and I'm not finding it now. Yes. So one more question regarding the number of documents retrieved from Pinecone based on query vector. How to decide what must be the threshold value to select the top n documents, how to decide on the n value. So this is, again, a very similar kind of question, right? Like, how do you make sure that you have the subset of relevant documents that are going to hit the user's query? And again, this is another opportunity to utilize tests and measure, basically, again, from the set of relevant documents that are relevant to a question, how many are actually being recalled, right? That will give you an understanding of what in general should be the number of documents that you should typically try and shoot for. So there's really no escape from having to create a labeled data set of known questions and known answers that you're expecting to get, and then measuring them over time and seeing like how your embeddings are actually performing against questions that you haven't seen before. Unfortunately, this is all we have time for. There are many more questions and I would love to answer as many as I could, but I'm going to ask any of you who still want to engage us in conversation to keep your questions coming to our community forum and engage us on Twitter. Myself and the other dev advocates at Pinecone, as well as people from Databricks, are sure to answer your questions as much as we can. Thank you so much for attending the session. Nathan, thank you so much for being here and sharing this really cool demo and all this content. I really had a great time. This was super fun for me. And that's it. Thank you, everybody. And we'll see you in the next Pinecone webinar.
Thank you. And we'll release the examples as well. So yeah, stay tuned.
Yes. Yeah, stay tuned.
Thank you.
Thank you so much.